Well, hello, dear students. So, this would be our concluding class or the last class of the chapter solutions. In fact, we have been learning a lot of things in this chapter, and today we are going to see an application of distribution law, which is having a lot of practical value. In fact, in organic chemistry synthesis or even the isolation of natural products from different sources, we use a protocol which is called solvent extraction. And this solvent extraction is is built or is developed on the principle of Nernst distribution law. So let us see what solvent extraction is. In fact, as you see, extraction means what? What do you mean by what do you mean by the process of extraction? Extraction is getting something out of the other. Like you're going to extract a metal from its ore, is it not? In fact, if I have to give you a bit funny example, if a tooth is taken out by a dentist, do you know the technical name for that procedure? It is called tooth extraction. So tooth is extracted from the gums probably. So extraction is like that. So what do you mean by solvent extraction? Solvent extraction is you are going to uh, get a solute in other solvent or in other medium into the solvent of your choice. That is what solvent extraction is. So basically solvent extraction means getting the solute from one solvent to the other solvent. So how does it work? It simply, you have the Nernst distribution law. That means a solute distributes between two solvents, two immiscible solvents. Now, uh, what is the what do I mean by the practical value of this? Okay, look at this picture. How do we do this practically? And for small scale solvent extractions, like we do in our laboratories, I'm not talking about the industrial scale solvent extraction, although solvent extraction is vitally important in industries also, natural product industries or industries with the pharmaceuticals. Any industry concerned with the organic preparation uses solvent extraction as one of its important industrial protocols. Anyways, how do we do the solvent extractions in our laboratories? You can do this in our laboratory also. For this, as I told you, in my previous class, that the immiscible liquids are studied using a separating funnel, a special apparatus called separating funnel. Now, let the separating funnel contain water or some water solutions. It can be a solution of HCl, it can be a solution of NaOH, basically an aqueous solution. Now, into that aqueous solution, you can put a organic compound. Okay. Now, this aqueous solution of the organic compound would solubilize organic compound to some extent. Okay, to some extent. Like for example, I gave you an examples of the solute like benzoic acid, which is more soluble in benzene and less soluble in water, but soluble to some extent in water also. So let us tell that I am putting benzoic acid into this water. Now, single layer of water, simple. How to do the solvent extraction? That means you have to extract benzoic acid into some other solvent of your choice. And mostly that some other solvent of your choice would be an organic solvent. Why I choose an organic solvent? For two reasons. One, organic solvent is immiscible with water. It forms a separate layer with water. And the other most important reason is the organic solvents most of the times dissolve organic compounds much better than the water. So you put ether layer. The common solvents we use in organic laboratories for solvent extractions is, one is the ether, the other is the ethyl acetate. Okay, so what is this ether? Diethyl ether. Usually we use diethyl ether. So C2H5O C2H5 or ethyl acetate. And now you put an ether layer, shake, agitate, and then what happens to the benzoic acid now? Where does it go? It goes into ether layer also, is it not? And if the dissociation constant favors uh, ethyl solubilization of benzoic acid more in ether layer, the solid benzoic acid distributes more in ether layer than in water. So that's how the distribution goes. Tap off the water layer, you take the ether layer. Now you what have you done basically? All the benzoic acid, not all, the benzoic acid which was there in water, you have got it now into the ether. So now how will you extract benzoic acid from ether or separate benzoic acid from ether? You simply evaporate ether. And the point about these organic liquids are usually they are all low boiling. You need not have to heat them too much. Like water is 100 degrees Celsius. Ether you can evaporate at 35-40 degrees Celsius. So you evaporate ether and the residue will be your benzoic acid. Okay. So the other advantage is you need not have to heat it for the evaporation process too much. Sometimes what happens if you are heating too much to evaporate your solvent, then compound could decompose also, is it not? Therefore, ether acetate can be easily evaporated. Now what happens? This is what the solvent extraction. What was the advantage? Benzoic acid was less soluble in water, more soluble in ether. So it came to ether fully. So what about the remaining water which you have collected? Do you think it is free of benzoic acid? No, it is not free of benzoic acid. Rather, it contains benzoic acid to some extent even. Fine. That is what the process of solvent extraction is. Now, how can you tell your solvent extraction is very successful? Oh, no, sorry, when is your solvent extraction very successful? Given the property of the solute distribution, is it not? So that's why I have given that statement. The greater the distribution ratio is in favor of the organic solvent, the greater will be the amount extracted in any one operation. So now, for example, let us think that benzoic acid is soluble equally between, no, okay, now let us keep benzoic acid aside. Let us take a solute is soluble equally between water and organic solvent. So is the extraction process good, better? Not better, because it will be present in the organic layer as well as in the water layer to equal extent. Even if you remove the water layer separately, lot of solute will be still present in water layer. Now let us see a solute distributes in organic and water layer where it is 100 times more soluble or 10 times at least more soluble in organic solvent. Then what happens? With the shaking and equilibration, lot of the a huge amount of solute, I mean appreciable amount, too much amount of solute will come into the organic layer. Why? Because it is 10 times more soluble in organic layer than in water. Is it not? Therefore, the greater the distribution ratio is in favor of organic solvent, better, good is your extraction process. I mean, of course, that was only a graphic. This is the real image of the extraction process. Can you see can you see a layer separation, a boundary between layers? You have the lower aqueous layer and the upper organic layer. More usually the upper layer will be organic layer because these organic liquids have lesser density than water. But there are few exceptions. If you are using chloroform or dichloromethane as your solvent for extraction, then they form the lower layer because their density is higher than water. But maybe in this example, it was ether or ethyl acetate as the organic layer. Can you see the color of the organic layer? Usually the organic liquids you take for extractions are colorless. But why is that red? Because you have extracted some compound which was red in color into the organic layer. Okay, and you can see the water. Maybe the solute was is too much soluble in the organic layer, so almost all of the solute has gone to the organic layer, so leaving the water layer colorless. But if you can examine closely, it is still pale, very pale red. That means trace amount of the organic compound is still there in the water. So now you collect the organic layer, you evaporate the organic layer, you are going to get that red compound. Is it not? You are going to get that red compound. Okay. This is how usually the natural products are extracted from the fruits, vegetables, or from animal sources. Now the point is this. In fact, I will give you an example like this. Now you're extracting a compound which is in water into an organic layer. For this process, I have given you 500 ml of organic solvent. What will you do? You can put that 500 ml of organic solvent at once, shake it, collect the organic layer, evaporate, and get the compound. So this is called a single extraction process. Why? Because entire 500 ml is used at once. Now, what I will do is, I will ask you to do this in a different way, in the sense, uh, divide this 500 ml into smaller volumes, maybe 250 ml 2 times or 100 ml 5 times, and do the extraction if you are using 250 ml 2 times, and do the extraction if you are using 100 ml 5 times. So this is called multiple extraction. What do you mean by multiple extraction? The same volume of organic solvent which you would have used for a single extraction, divide into smaller fractions and extract the compound using that smaller fractions multiplied by the number of times. This is called multiple extraction. But okay, see now, how is the multiple extraction done? You take aqueous layer, you add ether layer, extract it, collect the aqueous layer separately and ether layer separately. Now keep the ether layer separately in a beaker. The whatever the aqueous layer which is remaining, put it again back into the separating funnel and add one more aliquot of ether. Extract it again. For example, I have given you 500 ml of ether. You have divided into 250 ml, 250 ml twice. If I have to fit my explanation to this picture, you have divided into 250 ml, 250 ml, and you have done the extraction twice. You are not increasing the total volume of the organic liquid. What is that you are doing? The number of times extraction is done, you are increasing. So such an operation is called multiple extraction. Now, why this multiple extraction should be done? Why should be unnecessarily? Maybe why should we increase the number of steps? Isn't it laborious? Isn't it time consuming? Definitely it is. But there are several advantages of multiple extraction. The first advantage is you are going to extract the compound more efficiently in multiple extraction process than in single extraction process. Okay, so let us see why this multiple extraction is more efficient than single extraction. And there is no better way of seeing this than actually practically seeing how much of compound you are going to extract, considering a case. So let us consider a case like this. What is the case? The case is this. I have given you 100 ml of water and 8 grams of organic substance. So what have you done? You have dissolved 8 grams of organic compound in 100 ml of water. So in multiple extraction, the volume of water is fixed. That is 100 ml. You are not dividing into fractions. Which is the one you are dividing into fractions? The one organic solvent. That is what you are dividing into fractions. Okay. Now let us work out how much of our compound is extracted into our organic layer. Example, ether layer. In this problem, ether layer. If I do a single extraction, case 1, case 2, if I do a multiple extraction. Now, okay, let us work out the problem. All that you have to take is the distribution law formula. What is the distribution law formula? Concentration of the compound in organic layer divided by concentration of the compound in water layer is equal to K. That is what your distribution constant is. Okay, fine. Now, what is the concentration of the compound in the ether layer after shaking? That will be X amount of, you have taken 8 grams of compound in water. Out of that 8 gram, if you shake and allow it to settle, do you think the entire 8 gram will go into the ether? No, a fraction will go into the ether. How much of that goes into the ether is depending on the distribution constant. If the K value is higher, more amount will go into the ether. If the K value is lower, smaller amount will go into the ether. But definitely in any case, the entire A will not go into the ether. Okay. So how much will go into the ether? Let us put it as X. X out of A. I'll repeat this. X out of A has gone into ether. So how to find out the concentration of the solute in ether? Simply X by 100, because X grams is now in ether. 100 ml of ether divided by what is the concentration remaining in water? A minus X. Before extraction it was A. After extraction it is A minus X, because X has gone into ether. So the remaining will be A minus X grams divided by 100. So you solve this equation, you get X is equal to 2/3 A. Simple, yeah. So what is the percentage of the compound you have extracted? Initially it was A. Now A in water. Now in the ether it is 2/3A. So simply 2/3 means 66%. 66% of the compound has gone into ether. So simply putting, 66% you have extracted into ether in a single operation method. Now the same thing, let us work out for multiple extraction. How much of the organic solvent you are given? 100 ml. Divide that into two fractions of 50 ml each. So do the extraction first with the 50 ml. Same thing with the 50 ml. Take the concentration x1 divided by 50. Why am I differentiating it as x1? Because there will be two extraction processes. For the first extraction, the amount which goes into ether will be x1. x1 divided by 50. Please note the difference. Previous problem, it was x1 divided by 100. Sorry, x divided by 100, because 100 ml of ether you have taken. Now you have taken 50 ml of ether. So x1 divided by 50 divided by A minus x1 divided by 100. Solve this. You get x is equal to half A. Okay, half A. So what will be half A means? 50% extraction you have done. In the previous example, how much extraction you had done? 66%. Why 66% extraction was done? Because you have taken more volume of ether, 100 ml. Now you have taken only 50 ml. So 50% of the substance is extracted. Now what is the remaining in water? Because this is multiple extraction, right? The water you have to carry forward to the next extraction step. So what is the remaining volume, remaining amount of X in water? It will be 1/2A, half A. Why? Because half A has already gone into the ether, which you have collected separately. So half A. Now find out the concentration of, take this water, add another 50 ml of ether. This is the multiple extraction meaning. Add another 50 ml of ether. Total it was 100 ml, right? Divided into 50 ml each. You add another 50 ml of ether. So x2 divided by 50. What is the remaining layer? Remaining amount in water? Half A minus x2. Because even in this extraction, some amount will go into ether, right? So let that be x2. What is the concentration of compound in ether? X2 divided by 50. What is the concentration in water? Half A minus x2 divided by 100. Because the volume of water doesn't change. I told you in multiple extraction, it is the volume of organic solvent which changes. But in water doesn't change. It will be 100, still 100. So divided by 100 is equal to 2. Is equal to 2. Okay, yeah, fine. What is the 2 everywhere? I have written 2 here. Even in this previous example, I have written 2. Okay. Uh, what is this 2 here? Even in the previous example, I have written this 2. That is the distribution constant value, distribution coefficient value. That is important, right? Unless you know the distribution coefficient K, you cannot solve such type of problems. So K is equal to 2. Where did you get this 2 from? It was the information provided in the question itself. Where is that information in the question? We can extract, which will be provided. Its distribution ratio being twice in favor of ether. Please read the question. Its distribution ratio twice in favor of ether. That means it is K value is distribution ratio, distribution constant, distribution coefficient. All these three are the names of the same constant K. So twice means you take 2. It is 10 times means you take 10. It is thrice means you take 3. Or sometimes what will be given? K value is equal to 2.5, K value is equal to 1.6, like that. Okay. Now take that 2 here. X2 is equal to 1 by 4 A. So how much is extracted into the ether layer now? 25% was extracted. 25% of A. In the first extraction, how much was extracted? 50% of A. In the second extraction, how much was extracted? 25% of A. So if you club the ether layer of the first extraction, if you club means if you mix, combine the ether layer of the first extraction, and if you combine the ether layer of the second extraction, mix them. How much of A you have got after combining these two ether layers of the first and second extraction? 50% of A plus 25% of A. So you have got 75% of A. That means 75% of the compound you have extracted. The same procedure, you did it in a single extraction type. How much of A you had extracted? How much of compound you had extracted? 66% of A you had extracted. But what have I done? I have not increased the volume of ether. The same 100 ml, I have divided into 2 times. Then you have got 75% of A. So which one do you think better? Obviously, multiple extraction is better. Now, instead of doing it 2 times, if I had done it 4 times, I would have got it more than 75%. But you can go on doing like this for a number of times. So every time you are going to extract some amount of compound into your ether layer. So combine that ether layer, and finally the combined portion you evaporate. You will get your compound. Okay, that is fine. But how long should I do this to get 100% A? How many times multiple extractions I have to do to get 100% A? This is the question. Theoretically speaking, you cannot get 100% A because every time you do the shaking, some amount of A will still be in water. That is what distribution law is, right? Because it cannot be 100% solubility in one solvent and 0% solubility in another solvent. Some amount of A, maybe very minute amount, but some amount of A will be still left in water. Some amount of compound will still left in water. So theoretically, it is impossible to achieve 100% extraction. But practically, we stop at some point, at some satisfactory point. So, okay, anyway, I have extracted 99% of our compound. Anyway, let me stop. Fine. Okay. So that is what I told. It is not possible to remove the whole dissolved substance, however large the number of extractions may be. Okay, fine. Anyway, this is the continuation of my previous uh, working out of that problem. 250 ml of portion, 100 ml of portion I had taken for my extraction. Now, if I take 5 200 ml portions of ether, you will get 83.8% extraction. So either you increase the volume of now what are the changes I can make to get more amount of compound extracted? Either you increase the volume of organic solvent or you increase the number of times extraction is done. You expand or you increase the multiple extractions. Okay, now let us solve some simple problems related to solvent extraction. Okay, the previous problem, of course, it was a solved example, but that I gave you to make you understand multiple extraction is better than single extraction. Now let us solve a few problems which you find in your exams, easier ones, simple substitutions one. The distribution coefficient of x means a solute, some solute x for benzene and water is 10. That means what? It is 10 times more soluble in benzene. Find the amount of X extracted if 1 gram of it dissolved in 100 ml of water is equilibrated in a separating funnel with 100 ml of benzene. So all that what you have to do is first write the distribution for constant law formula. Concentration of X in benzene divided by concentration of X. X means solute in water is equal to K. What is that K? 10, because they have told it is 10 times more soluble. They have given distribution coefficient of X is X of for benzene and water is 10. It's the information in the question is equal to 10. Now, all that you have to do is, if that I discussed in my previous also, you have to simply find out the concentration. What is the concentration of X in benzene? It is X by 100. What is that small x? Out of 1 gram, small x gram has gone to benzene. How much has gone X? That is what you have to find out. Divided by 1 minus X by 100. What is it? Why is this 1 minus X? Because it is stated as 1 gram. In our previous example, we had taken it as A minus X, capital A minus X. Why? Because the amount was not given actually how much gram was taken in water. It was simply told A gram was taken in water. But here the amount is specifically given. 1 gram is taken in water. So I will write it as 1 minus X divided by 100. Why am I dividing by 100? Because that's the volume factor. The gram is not concentration. Gram divided by volume is the concentration. So solve this equation, find out the value of small x. So it comes that x is equal to 0.909 grams. So that means what? Even with a single extraction in this example, some 90% of the compound you have extracted into benzene. Because it is 0.9 grams. The answer is 0.9 grams. So converting to percentage, it will be 90% you have extracted into benzene. But in our previous example, with a single extraction, we had extracted only about 66%. Why it is 90% here, even with single extraction? Because there the K value is 2. Here the K value is 10. Remember my previous statement. Higher the K value in favor of an organic solvent, better is the extraction. So 10 times more soluble in benzene. In the previous example, our solute was 2 times more soluble in ether. Probably if something is 100 times more soluble in organic solvent, single extraction will almost extract 99%, 99.99% of your compound. But that the combination is difficult to find. Sometimes rarely you can find. Usually we work between 1 to 10. Okay. One more problem I have solved. This is regarding multiple extractions. The same thing. You can read this problem. There you have 3, K value 3. I'm just taking out all the information from the question, writing it directly. K value is equal to 3 because it is given 3. Coefficient is 3 at 25 degrees Celsius. 4 gram of isobutyric acid was taken in 100 ml of water. And 100 ml of ether was used for extraction. Now, we have to solve this problem in a similar line like we solved in our previous question. What would be the effect if 2 successive 50 ml portion of ether was used for extraction instead of single extraction? So how to solve? First, you do it for single extraction. And then you have to do for 2 extractions, 50 ml each. You find that with single extraction, you extract 75% of isobutyric acid. With 2 extractions, you extract 84% of isobutyric acid. So again, multiple extraction is better than single extraction. Now, this is fine. Now, okay. Anyways, even in your exams, you don't get questions where find out the amount extracted after 4 extractions like that. You usually ask for 2 extractions. But now, let's think about a practical scenario. Why? Because now 5 times I've extracted. Yeah. So how to do this? How to solve this 5 times? 5 times I have to expand my problem. That much expansion should be there in our problem. 5 times I have to repeat the problem of our solution. Sorry, 5 times I have to repeat the steps of the solution. Same steps of the solution. 5 times I have to repeat, but different way, different concentrations. Every time the concentration of X will be reducing. So to simplify this, we also have a general formula. What is that? Xn is equal to A Kv divided by Kv plus small v to the power of n. So what are the terms in this formula? What is this general formula? This general formula is the formula to find out the substance which is left unextracted in water after the number of extractions n. In all our previous 2 examples, that small n would be 2 because we spoke about 2 extractions. What is the capital K? Capital K is nothing but the distribution coefficient. Capital V is the volume of water, aqueous solution you have taken. Capital A will be the gram of organic substance initially you have taken in water. And small v is the volume of organic solvent you have taken. What is the capital N? It is the what is small n? It is the number of extraction. You can use even this general formula and solve the previous problem also. Okay, so this is about the solvent extractions and use of solvent extractions for extractions of use of the solvent extraction method for extraction of organic compounds. So this completes our discussion on solvent extraction. So basically what we have done in solvent extraction, What is solvent extraction? We have seen. What is a single solvent? Single extraction means, multiple extraction means. And we have numerically, by solving numerical problems, we have proved that multiple extraction is better than single extraction method. And finally, we arrive at a general formula to find out the amount of compound which is unextracted after the number of operations n, small n. Now we will go into one simple application of this solvent extraction, not in organic chemistry, but in inorganic chemistry. Because all these things I have been talking about organic chemistry. Right now, let us take an example for inorganic chemistry. You will be doing this inorganic salt analysis. I think you have done in your PUCs also. How do we do a confirmatory test for bromide? Br minus. So what is the preliminary test for bromide? You take the salt, make salt, and then add concentrated H2SO4. You get reddish brown fumes. Then it is brown, or orange fumes. Then you get bromide preliminary test. The confirmatory test for that is, to that salt you take a fresh salt sample. To that salt sample, you are going to add chlorine water. This chlorine is an oxidizing agent. It oxidizes Br minus if it is present in your sample into Br2. So the bromine gas is liberated. But this bromine gas is not that much soluble in water. So what you do, you take chloroform, organic solvent, and shake this. The name of the confirmatory test is orange globule test. What is that globule? Globule is the chloroform layer which is present below water. Now, bromine goes into chloroform and makes it orange in color. Why bromine goes into chloroform? Because bromine is more soluble in chloroform than in water. If you do this in a separating funnel, it becomes an extraction. But if you do this in a small test tube, it becomes a test. Okay. So for that, you can see orange globule formed after shaking, after adding chlorine water to your salt sample. This is the confirmatory test for bromine. So how is this extraction? You are actually extracting bromine which was present in water into your CCl4. Okay. Large scale separating funnel, small scale test tube. But still you can find that orange globule distinctly visible. One more important application of this distribution law, not the solvent extraction, distribution law in total, is the partition chromatography. I mean, you have learned this chromatography in your first semester, maybe. So I am not going to elaborate on this. You know the principle even. There is a stationary phase and there is a mobile phase. Stationary phase, initially, your compound which has to be separated is adsorbed on the stationary phase, and the mobile phase is running on this stationary phase. Usually stationary phase would be silica gel and the mobile phase is an organic solvent. So if the compound distribution coefficient is important, between what? Between two phases. Which is the two phases? One is the solid phase, stationary phase, the other is the mobile phase. Till now, in all our examples of distribution law, we were taking liquid-liquid separation. But here it is solid liquid separation. Solid is one phase is solid, the other phase is liquid. In our previous examples, both the phases were liquids, immiscible phases. Here the immiscible phase, one phase is solid, the other phase is liquid. You can do like this also. So distribution wise, initially it was given for liquid-liquid system. Now, and then with the discovery of chromatography, it was extended to solid liquid systems also, immiscible systems. So our solute, which is the compound we have to separate, is now in the is now distributing between solid phase and the liquid phase. Now I have taken two compounds A and B. And my task is to separate A and B. How to separate them? I will run this mixture of A and B through a column of silica gel using an organic solvent. So what happens? The compound which is more soluble in mobile phase or whose distribution coefficient K is higher in favor of mobile phase, that comes out first from the column. Is it not? Because it is more soluble in our organic phase, it dissolves in organic phase and comes out first. The less soluble organic compound, or simply putting, the compound which has less value of K in favor of organic mobile phase, will more stick to the silica gel, but doesn't mean that it will permanently stay with silica gel. For that, you have to use large volumes of mobile phase and longer duration. Finally, it comes out. But the one which is readily soluble mean mobile phase comes out first. So take that and then collect them separately. So see, I have just simply told you a gist of partition chromatography. You have learnt it in detail in your previous semester. Okay, so I think this will conclude our all discussions for your semester syllabus on the chapter solutions. So next chapter we are going to take up will be phase rule. Okay. Anyway, thank you very much for listening and watching all my videos and attending all the classes with respect to the chapter solutions. Thank you very much.